Hello, Mr. Ryan, are you right? Right. So a few days ago we talked about the bus station. Remember that the bus stations are in a circle. Yeah. A simple graph. 0, 1, 2, 3. If the cost 1, 2, 3, 4. Okay, let's make this bigger. If this is 9. So what's the shortest distance between 0 and 1? This is a graph, right? A regular graph. Right? We talk
it
about
doesn't matter because both ways.
Oh, both ways, yeah, exactly. Okay, how about 19th?
Bottom.
This way, yeah.
That's impossible because
What?
19 and 3 are about the same level.
Okay. When we talk about the graph, we don't actually look at the distance, especially this is the weighted graph, right? So this is a simple regular graph. We talk about a regular graph. Regular graph means that each vertex has the same number of neighbors. Right? And for this particular graph problem, we can just use the math. The shortest distance, there are only two ways, right? Either it's this bit or it's this bit, right? So we can just do a simple math. We talk about that. Since we can treat this as a weighted, undirected graph, then we can use the graph algorithm, the shortest path. We talk about lots of shortest paths, yeah? Dijkstra. These can be used on directly or indirectly, weighted or unweighted graph, right? But it does not work on negative weights. We talk about Floyd, Warshall, uniform cost search, right? This is the variant of this. The DFS does not work in this case. Why is that? The depth search and breadth search does not work in this particular case. Why is that? Anybody?
Unweighted.
Unweighted, yes. So depth search and breadth search can only be used on unweighted graph. Okay? So that means that we cannot use these two algorithms to do this, right? And we talk about iterative deep learning search, which is the combination of depth search and breadth search. Yeah? Okay, so we can use these three shortest path algorithm. Okay, so let's use this Floyd Warshall. Right? When you talk about that, let's just review this by solving this problem. Right? The Floyd Warshall is OV cubic. Shortest path algorithm can be used on weighted or unweighted graph, directly or indirectly graph, and it's multi-source. Meaning that when we perform this shortest path algorithm, we can get the shortest path for any pairs. So we have this Dij. Is represent the shortest path between the vertex I and vertex j. Okay. The spirit of the Floyd Warshall is this, right? Vertex I, and then we want to update the shortest path between the vertex I to vertex j, and we keep updating this, keep iterating the vertex k. If the distance Dij, right? If Dik plus Dkj, right? Look, we talk about this. If it's smaller than Dij, then we can replace the distance, the shortest distance from I to j with this path, right? Look, this I to j may be a subproblem of a bigger path, of a longer distance. For example, if this distance A to B. If the shortest path, look, we want to calculate the shortest path between A vertex and A vertex B, right? And at some point, we realize that the distance to I from I to j can be replaced by I to k plus k to j, right? So then we just abandon these, right? Am I right? So we can just replace this with this, because this one is a subproblem and it provides a shorter path, a better result. Okay. So in order to apply this algorithm, we need to convert these into a graph, into this, right? And then we can apply it, okay? Apply this Floyd Warshall. So this Floyd Warshall is multi-source, OV cubic. Compared to Dijkstra is OH plus V log of V. Which one is bigger? Which one is faster?
The right one.
This one is faster, yeah? Because Dijkstra makes assumption that all the weights are positive. So it's kind of greedy, right? Remember the Dijkstra algorithm, two-step. Update the estimate and pick the next vertex with the smallest weight in the unexplored set, right? So it's based on this assumption, so it's very greedy. So it's and if we implement it using a priority queue, is the time complexity is OE plus V log of V, because the log of V comes from the step extracting the minimum, the optimum from the priority queue of heap. The Floyd Warshall is multi-source, and it works on negative weights as well, right? It works on negative weights, so it's slower. But the advantage of this Floyd Warshall is that it can be used to compute the shortest path between any two pairs. It's a multi-source. This is a single source. Okay, single source means that the output of Dijkstra produce this D array, right? So from 0 to n, that gives the shortest path between the source to any other vertex. Define the shortest distance. And then we given the distance of the array distance array distance I is the shortest is the distance between vertex I to vertex I plus 1, right? So we need to convert these to the graph, and we want to get a just distance between star to the end. So first of all, we need to use the d. So the number of vertex, length of the distance. So then we can construct this D array. D array, this is the D two-dimensional, Dij, right? We want to have this Dij, this is two-dimensional. D equals, at the beginning we set it to infinity, times n, 4 underscore in range n. And then this gives us Dij. We set the initial value, Dij, to infinity, right? So what does it mean? It means that, look, if we have this, remember the bus stop, right? The bus stop, 0, 1, 2, 3. If we do this, it means that we haven't put the edges in. So the distance between any two vertex is infinity because we haven't added the edge. Now we want to add the edge. So we just go through it. For I in range n minus 1, we skip the last one because the last one has a connection to the first one, right? So now di I plus 1 equals di plus 1 I equals distance I. Okay, so basically this means that we set the distance I. That's the distance between these the neighboring vertex, right? And di plus 1 equals di plus 1 I. It means that it's undirected, right? The distance between these to this is the same as the distance between these to this. That's what it means. And then the last step is to add the edge of this one. So di0 actually is d0 n minus 1, right? d0 n minus 1 equals d n minus 1 0 equals distance. Distance, the last one is minus 1, right? We have constructed edges, right? For k in range n, right? And then for I in range n. For j, this is what the ov cubic comes for, okay? In range n. Dij equals the minimum of Dij. Yeah? This is basically dynamic programming. Dik plus dkj, right? We keep updating. So basically the outer loop is to iterating each vertex, and then the inner two loop is to iterate any pairs. So we're iterating any pair I to j, right? And then we iterate another k. So if we find a shorter path by going to this, by jump to k, I to k distance plus k to j, then we can replace I to j with this shorter path. Right? That's what it means. Then return, we just return distance star to the n, right? And then you give the answer ov cubic. And we talk about the product, iter2 product function. Right? So this bit can be replaced by for k I j in iter2. From iter2 import product and range n repeat equal 3. Okay, so range n Cartesian product excel 3 times is the same as this for loop. Right? The time complexity is OV cubic. The space complexity is OV squared. Why we use the two-dimensional array. Okay? The bus stop problem is a regular graph, with a circle, the vertex in a circle, right? The bus stop problem, right? We're talking about a math problem just to compute the minimum of two paths. Right? Distance between any two bus stop vertex can be only two ways, right? Right? There are only two ways because they form a cycle. Yeah, it's a regular graph. Today we're using this Floyd Warshall. We talk about that. This is the multi-source shortest path algorithm that works on directed and indirectly weighted or unweighted graph. And the weights can be negative as well. So basically this is a very, very powerful algorithm. It works on many, many scenarios. One disadvantage is that it's slow. It's OV qubit. Right? This can be visualized as a graph program, and we can apply the shortest path algorithm to it. Can we use the Dijkstra algorithm to solve this problem?
Yes.
Yes. Yeah. Well done. Okay.
So we have this graph.
Yeah. Yeah.
And we have
cycle.
start and destination.
That's right. Yes.
And numbers.
Yes. And what are we trying to do?
Find the shortest path.
Shortest path.
Okay. Yeah. We are trying to find the shortest path.
distance.
Shortest distance between any two bus stops. So what's the algorithm we are using today?
Floyd
Warshall. Floyd Warshall. Yeah. It's a multi-source. Okay. Bless you. Okay. That's it for today. Bye bye.
Bye.
Bye bye.